All right. We're going to find sample spaces and probabilities of compound events. Then we're going to find the sample space of two or more events. I can find the total number of possible outcomes of two or more events and find the probability of compound events. For starters, let's look at this. One lock has 3 wheels. Each wheel is numbered from 0 to 9. How many possible outcomes are there for each wheel? This is an important question because many people think that there's just 9 possible outcomes. However, there's 10 because it's 0 through 9. So there's 10 possible outcomes. Well, how many possible combinations are there? Well, if we think this through, we could have 10 different numbers on each of these slots. Now, just reasoning through here, you should be able to stop and realize that if you could go from 0, 0, 0 to 9, 9, 9, and that would be 1,000 combinations. I want you to look at these 3 numbers here. Is there any way to take 3 tens and turn them into 1,000? We'll talk about that. Another lock has 1 wheel numbered from 0 to 39. Each combination uses a sequence of 3 numbers. How many possible combinations are there? So this one, a little bit more tricky because we could have 0, 0, 0, all the way up to 39, 39, 39. And there's 40 possibilities for each number, and you've got to choose 3 of them. So if we look back over here, maybe by now you realize that 10 times 10 times 10 is 1,000. So we can do 40 times 40 times 40. And so 40 times 40 times 40 gives us 64,000 possible combinations. So what we kind of played around with there without defining the terms was a sample space. It's the set of all possible outcomes of one or more events is called a sample space. You represent a sample space using a table or a tree diagram. We will most often be using tree diagrams. You randomly choose a bread and a type of sandwich. Find the sample space. How many different sandwiches are possible? So our breads, I'm going to use W for wheat and S for sourdough. And then the type. So W for wheat, S for sourdough. I've got H for ham, T for turkey, ST for steak, and then C for chicken. So the wheat, we could have a wheat, ham on wheat. We could have turkey on wheat. We could have steak on wheat, or we could have chicken on wheat. On the sourdough, we could go ham on sourdough, turkey on sourdough, steak on sourdough, or chicken on sourdough. So if we look at this, this is built our sample space. And if we look, we've got 1, 2, 3, 4, 5, 6, 7, 8 sandwiches. So our sample space is this, and the different types of sandwiches are down here. Okay, so now the fundamental counting principle. We hinted at it back at the first problem with combination lock. You can use the sample space or the fundamental counting principle to find the total number of possible outcomes of 2 or more events. An event M has M possible outcomes. An event N has N possible outcomes. The total number of outcomes of event M, followed by event N, is M times N. And we can see that back here. There were 2 types of bread and there were 4 types of meat. 2 times 4 is 8. So there were 8 sandwiches. So let's look at this one more time. Find the total number of outcomes of rolling a number cube and flipping a coin. So here we can roll a number cube and flip a coin. Well, rolling a number cube, we've got 1, 2, 3, 4, 5, 6 on a number cube. And then we've got either on the coin, we've got either heads or tails. So we could say 1 head, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, and then we could say 1 tails, 2 tails, 3 tails, 4 tails, 5 tails, 6 tails. And what we could do when we see that sample space is we could see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 ways of rolling a number cube and flipping a coin. Or we could have cut to the chase a whole lot faster. There's 6 outcomes on a number cube. There's 2 outcomes on a coin. 6 times 2 is 12. And that becomes even more important when we look at this. In a closet, there are 7 t-shirts, 4 pairs of jeans, and 3 pairs of shoes. How many different outfits can you make from t-shirts, jeans, and shoes? So we've got 7 t-shirts times 4 jeans times 3 shoes. So we're going to multiply those together. So 7 times 4 times 3, that gives us 84 outfits. So a compound event. A compound event consists of 2 or more events. As with a single event, the probability of a compound event is the quotient of the number of favorable outcomes and the number of possible outcomes. So favorable divided by possible. So back in example 2, what's the probability of rolling a number greater than 4 and flipping tails? Well, let's look. Number greater than 4. Number greater than 4 is 5, and tails is 5 right down here. So we've got 5 and 6. And so we see that we've got 2 out of 12. And so 2 out of 12 is 1/6, and 1/6 is roughly 1.67%. Mr. Manchester, how'd you know that? Okay, 2 divided by 12. Whoops, that was 2 times 12. Whoopsies. 2 divided by 12 is that times 100 is 16.7%. Now, so that's where these tables to draw our sample space does come in handy, because otherwise we'd be left going, well, how many of those 12 fit that description? So tables and trees can be helpful. In example 2, what's the probability of rolling at most 4 and flipping heads? Now, at most 4 and flipping heads, going to change color here because we need to see this in a different color. At most 4 is here and heads is here. So we're looking at these. So there's 4 possibilities. So there's 4 out of 12. And 4 out of 12 is 1/3, which you hopefully maybe have memorized by now is 33.3%. Modeling real life. Last problem. On a game show, you choose 1 box from each pair of boxes shown. In each pair, 1 box contains a prize, the other does not. What's the probability of at least winning 1 prize? So there's several ways of doing this, but it might be easiest to go ahead and do a tree diagram of just what we want. So we want the probability of at least winning 1 prize. So we're looking at, in the first choice, we could win a prize, or we could not win a prize, or we could win a prize in the second choice, or in the third choice, we could not win a prize, or we could win a prize. Over here, we could not win a prize or win a prize. Again, in the first choice, we could not win a prize, but then we could not win a prize or win a prize, and then we could not win a prize or win a prize, and then we could not win a prize or win a prize. So now if we look here, it's a probability of winning at least 1 prize. So I have a little bit of extra experience with this, and so I notice that winning at least 1 prize is the fancy word is compliment. And I don't think we're going to use that word this year, but the fancy word is compliment. The complement, the opposite of that, if you will, for lack of a better word, is the probability of winning no prizes. If you don't win any prizes, you haven't won at least 1. So if we look here, this is the probability that this is the only case where you do not win any prize at all. So if we look, we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 possible outcomes. In them, only one outcome doesn't win at least one prize. So that is 7 outcomes that do win at least one prize. So we want 7 divided by 8. 7 divided by 8 is 8.75 times 100 is 87.5% chance of at least winning one prize. So the hope is that you guys can then go practice these and be successful on your own.